Hello everyone, welcome to the Akrodyn YouTube channel. Today I will show you how you can build your own alcohol sensor using MICS5524 sensor module. Here you have an overview of what kind of gases you can actually detect. We want ethanol, so you see here on the bottom there is the concentration in parts per million. And R0 is the calibrated internal resistance of the sensor module, which you get from air calibration. And RS is the new detected internal resistor after it detects a gas or exposed to gas. So I already started with the schematics. So we are using an ESP32C3 Mini. So it's a microcontroller with integrated Bluetooth and Wi-Fi. It is also pretty low power when you know how to set it up. Then we're using a USB interface so we can flash the microcontroller. It could also be used, for example, charging a battery. Then we are using this inrush current limiting IC, and it's also a power switch. So it chooses under normal condition the USB when plugged in, and otherwise it will use the 5-volt provided from a battery. The battery is a 9-volt block battery. It has here some input protection, on-off switch, some inrush current limiting, and then goes to these two buck converters, one for 5-volt, so that will be used for the sensor itself, and one for 3.3-volt, which is used for the microcontroller. The alcohol sensor itself is turned on by a digital switch, so you can save a lot of energy when the device is still turned on and not used. So this will switch on the power to this heating loop here, and after around 10 seconds, the sensor should be ready when calibrated for air already. Here is the voltage divider for the measurement sensor. We also added a output buffer stage for high impedance input, so you do not disturb in the end your voltage divider with an additional parallel resistor. And here is a little output filter. It's like a charge bucket, so that the SAR ADC will not disturb the buffer itself. As an indicator, we either use Bluetooth, so you can have your actual alcohol level or Bluetooth streamed, and we have these LEDs that gives a rough indication what your alcohol level is. So it's three VS2812B LEDs, which can be digitally controlled by only one line. So yeah, let's first start with one of the buck converters. In the end here, it's extremely crucial that you have low inductance in the input loop and low inductance in the output loop. So let's see how we can arrange this. So when designing a buck converter, you need to be careful about your inductance of the high-speed current path. In the end, you have like from the input capacitor, the high side fed to the C out and back the loop area, and the loop area designs in the end your inductance. So this should be minimized, so the area should be minimized. When we look at our design, it's like this loop here for the input. In the end here on our design, it's something like this here. So that has then minimum inductance. So I arranged the components as I think, yeah, is a really good minimization of this loop area. Then we have the second one, which is when the low side switch is turned on. This is like this here, and this is here. So that should be pretty much minimized. So now we will continue with arranging the components. So now that we have arranged all the components, we can start with the routing. So the easiest way to do is just auto route all, and we are done. Since we have some high-speed signals like USB, we will use a 4-layer PCB with impedance control. So what you need to do is to adjust your design rules and your layer stack up. You go to your manufacturer. For us, it's just a PCB. Then you choose in the end your 4-layer stack up you want to manufacturing according to. For example, we now take the 3313 stack up, and you see how the distance for the pip rack and the inner layers in the core should be. You also choose the pip rack types with the dielectric constants. So you go into where is it? Design layer stack up manager. Then you have the stack up here, and you just copy paste what you have from your manufacturer. So here it's. So now you go to your design rules, and you can use the impedance matched profile or just add it to the preferred width. So you can take your 50 ohm traces only where you want them. For the USB, you add it like a net group, and then you can choose your impedance profile here. So then it's automatically only allowed to use the impedance match traces. So now we will route. Okay, now we are done with the PCB. We can add some teardrops here to get rid of thermal tensions. So repour polygon, make the DRC, and we are fine. So yeah, thanks for watching this video, and we will soon post the next video about the verification of the sensor calibration and all that stuff. See you soon.